Good afternoon, everyone. Thank you for coming to another systems engineering seminar. Today is a great pleasure for me to have Professor Kyriakos Vamvoudakis. Professor Kyriakos Vamvoudakis received his diploma, which is equivalent to a master's degree from the Technical University of Crete in electronics and computer engineering, and then his master's and PhD degrees from the University of Texas in Arlington, working with Professor Frank Lewis. After his graduation, he joined University of California in Santa Barbara, working as a research assistant for between 2012 and 2016, and then Virginia Tech as an assistant professor between 2016 and 2018. Since 2018, he has been with the Faculty of Aerospace Engineering at Georgia Tech, where he is the current Detton and Dukov endowment professor in aerospace engineering. He has received numerous awards, including the Young Investigator Award from the Army Research Office, the NSF Career Award, the Minerva Research Award, among other things. It would take me a lot of time to go over the list of decorated list of Professor Vamvoudakis' resume. His research has been awarded several Best Paper nominations awards and other significant recognitions. He has a very rich involvement with the editorial board on the majority of the journals in learning and control. So if you have submitted a paper in learning and control, most likely this is being handled by Professor Vamvoudakis. But most notably, he is associate editor in Automatica and IEEE Transaction Automatic Control, which are the two flagships journals in controls. He is a member of the Technical Chamber in Greece, IEEE Senior Member, and Associate Fellow in AIAA. With this, please join me in welcoming Professor Vamvoudakis today.
Thank you very much, Andrea. It's a pleasure to be here, and thank you everybody for being here. So I met Andreas many years ago when he was still at the National Labs, and since then we have been really good friends and collaborators. Actually, we have also even a grant together working on the intersection of model-based and model-free techniques. So it's always good seeing him and interacting with him. Okay, so the talk, I will try to bring different ideas from different domains. So my lab is called Intelligent Cyber-Physical Systems, and my work is on learning-based control and security. So I will try to bring all these ideas in something that I will call data-driven sensor and actuator selection for intelligent, complex, adaptive systems. So cyber-physical systems, I guess in this audience I don't have to talk much about what is a cyber-physical system. And I'm sure if you took Andreas' class or you're working with him, you know what a cyber-physical system is. But again, I want you to get the message that cyber-physical systems are very difficult to model because they're highly complex and interconnected. And of course, it's a combination of physical, computational, and communication components. And a cyber-physical system is anything. It can be things from military, smart grid, healthcare, autonomous driving, and so on and so forth. So even your own body is somehow a cyber-physical system. So of course, as we increase complexity and the systems they become smarter and smarter, this increases the uncertainty across multiple layers. And then this gets me to why we want to work on this topic, because there's lots of data, okay? So how about if we use this data to do actuator selection, sensor selection, or actuator allocation. And all of these things, you will see what exactly they are, but they will happen in real time by using something that you will see we call a reinforcement learning. And so most of the things that we will describe, they will follow these very simple feedback mechanisms where we will have an unknown system over here, okay? Our controller, we'll call it the actor, and then a critic, which actually will tell us how good our controller is. Again, you can think we're playing in a movie, right? So you have many actors, and then you have a critic. So the critics will tell you how good you're performing, okay? Okay, so before we see how we can do actually actuator and sensor placement, of course, what is an actuator? So here's some actuators from toys for now, okay? So the device actually that implements your control input. So whenever you design a control input, this actually moves something around, okay? Which in a toy example, it looks like that, okay? So, but of course, if you connect it to your controls class 101, right? So this is actually a column of the B matrix, right? If you have a linear system, okay? So if you have a linear system from x dot equals ax plus b u, okay? So the column of the B matrix actually tells you the actuators, okay? And your u actually will move those actuators. Okay, so let's actually describe the first part of the talk, which is an actuator selection. So, actuator selection, why we want those? Okay, the actuators, again, from your class, again, these are the implementation of the control inputs. They have to guarantee a sufficient level of controllability. Okay, so again, you have to make sure that controllability, I'm able to control my system when I go from point A to point B. Okay, and of course, my research also takes care of resiliency, and this resiliency can be to faults, attacks, and failures, and so on and so forth. And of course, I want to do that given that I optimize the performance. Okay? So these are the three important things that I need to take care of when I do actuator selection. So, of course, everything though is model-based. So if you check any paper on actuator selection, this is actually a very hard problem because the complexity increases with the number of actuators. Okay? And of course, the complexity increases even more when you have to describe the model in a dynamical system way. Okay? So let's see how we can avoid doing that. So again, as I said before, in CPS, in superphysical systems, the systems are unavailable, or they might be inaccurate, okay? Or they can be time dependent, okay? So they change over time. That's why we want to do something, namely an actuator selection, that doesn't involve the system models, okay? So then this gets me to the magic word here, which is called data-driven, okay? Okay, so let's actually start putting some math now. Again, we have done it for linear and nonlinear systems, but of course in linear systems, you have a closed-form solution, you know how to compare it, you know it's actually correct. So let's go back to our 101, right? So you have a classical dynamical system where X is the state, use the control input, A and B, of course you know what it is, right? So the drift dynamics, the input dynamics. So let's see if we had it as a model, if we had the model, let's see what we can do. So when you do actuator selection, right? So remember what I told you, each column of the B matrix is an actuator, okay? So what we want to do is we have a fixed component, okay, which we will call it B0, that the actuators that are already part of the system, and then you have another component, which we will call it B mathcal B, okay, where are the actuators that they need to be selected, okay? So why, again, somebody will need to select these things? Because of these things. Controllability, resilience, that's what we can use. So when I put more actuators in the systems, then I can get more controllability, more resiliency, and so on and so forth. Okay, let's go back to the math. Okay, so again, I start with P0, and I'm going to play with this matrix here. Okay, so again, this is our problem for now, okay? So I want to choose these actuators here. Okay, so let's see actually what we mean. Again, we have a pool of actuators, okay? Let's say there are n of them, okay? And I want to select the best of them, okay? So in other words, case a subset of n, and I want to select the best of them to incorporate to my system. So what we want to do then, if I want to select the k best of them, so then I have to maximize the controllability, right? So every time I want to incorporate more actuators into the system, I want to find a way to maximize something that quantifies controllability, okay? And of course, I want to do this optimization given that I have to pick k of them, okay? Very simple optimization. Okay, so, and then of course, after finding this optimization, we solve it for B, okay? Then I can set this B mathcal V there with these actuators, okay? Any questions? Okay. Okay, so now, let's see actually how we can quantify controllability. So again, we go back to our optimal control classes, and we say, okay, so I will define a minimum energy problem. Okay, and here you see that I only have the U here. Okay, so and I do that define horizon given my dynamics, initial and final condition. Okay, and of course, as you can expect, more controllable systems, they have smaller optimal values, right? Because I optimize this. Okay, so of course, as I said, we have very beautiful closed form solutions. This is well known in control, okay? Because in linear systems, you have these beautiful closed form solutions. So the optimal value, if you solve this problem, is given with this one, okay? So again, XF is the final, right? And then everything else is just pretty straightforward. And of course, in order for me to solve that, I have to get this Q inverse, which of course, you know, if the system is controllable, I can find this Q inverse, and this is the controllability grammar. Okay? So, let's see. Let's try to, for now, I will try to model this f of b. Okay? So, the Gramian. Let's see what I can do with the Gramian. So, this Gramian will quantify how good my B matrix is. Okay? Because I put the different components there, and then the value of this Gramian will quantify how good my B is. Okay. So, as you can expect, you see Q inverse, a larger Q is better, a small Q is worse, as you can expect. Okay? So, if I want to maximize something, right, let's check that f of b that I want to optimize for my actuator problem to be the trace of this controllability graph. Okay? So eventually, if I have the model, what I will do, I will take this, I will put it here, then I will do my actuator placement problem. But of course, as you can see, this requires all the Greek alphabet, like alpha, beta, okay, or AB, as you can call it. Okay? So now, let's say, so as of now, okay, for now you will see that I will motivate through the model-based framework, and then I will do the model free. Okay, so I will maximize this trace, okay, given that my final time still is free. Okay, of course, if my final time is infinity, as you can expect, then I will converge to this algebraic one. Okay, so of course, as you can see, no integrations are involved. Okay, before you remember I had my integrations, right? So what I can do here, I can solve it for Q. Boom, ready, right? Okay, so one problem here, right, is, as of course you know from the open control class, in order for you to solve this equation, okay, you need to have a Hurwitz. Okay, so a Hurwitz means all my eigenvalues are on the left half plane. But not always the case. Okay, so if it is not, right, you can always move them around. Okay, by using this this movement of the eigenvalues. So let's say I can always have the freedom of moving the eigenvalues even from the right half plane. I can use this weighted Gramian, and I can move them on the left half plane. Okay, so we'll see what happens. Okay, so again, as you see here, okay, I have this problem now, okay, that eventually I know what this f of b that you saw before is, but again, solving this requires knowing A, right? A and B, okay? So let's see what we can do more. So we can be inspired by reinforcement learning, as you saw before. So, and what I want to do is, I want to find a way, I want to find a way to solve this Lyapunov equation forward in time, okay, and without requiring A and B, okay? So, let's see. For now, we know that when I want to reinforcement learning up to now, it can solve some specific form of Lyapunov equation. So you see that I have these little boxes here. Why? Because the transposes are on the wrong way, right? So A transpose P, plus PA and so on and so forth, okay? So every time you want to solve a Lyapunov equation with reinforcement learning, okay? So what, you have to have it in a specific form, okay? So this one doesn't follow the form, okay? So again, the Lyapunov equation is A transpose P plus PA plus blah, 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 okay? So now, wrong term, wrong, okay? So let's see how we can actually start working on this one, okay? So for now, of course, we can, as I said, we can try to see, okay, what is the model-based, and then try to bring it to a model-free framework. Okay, so this is just a straightforward flow-from solution for the theorem if we had the model. Okay, so what you want to see here also is that if your A is Hurwitz, right, you have the P there, but if your A is not Hurwitz, then you move them around, as I told you before, right? So this gamma is when I move my eigenvalues on the left-hand plane by using this weighted grounding. Okay? Okay. So, again, remember that this one, which is in the correct form, okay, is almost the derivative of x. Okay? Almost. So, let's see what we can do. So what we want to do here is I want to put my unknown components, okay, in this vector, half vectorized form, which is P gamma. Okay, again, whatever I don't know, I put it in an unknown vector, okay, or whatever I want to estimate, okay, and then I use all my combinations of my states, okay, I use it as my basis, okay, and eventually I can solve this, okay, I can call it as a temporal, so this is true, okay, even if you know the dynamics, and this is 0, okay? So if you don't know, though, and you want to approximate it, so then this is defined as a temporal difference error, okay? And then eventually you can solve it. So for now, what we did here is we wrote it in a form that will help us navigate reinforcement learning. Again, I put the one that I have to find, okay, in this half vectorized form, so this is half vectorized form, okay? So in other words, this means is I stack the components of a matrix on a vector, and then I take out the symmetric ones, okay? And then here, this one, okay, is just a Kronecker product of different instances of the state. Okay, so this will serve as a basis. But again, this is nothing apart from a Bellman equation in an integral form, okay? So, again, of course, what you can do here, I can solve it, right? The only unknown here is this one, right? So I can solve it, boom, I'm ready. I can use least squares, recursive least squares, anything you want. If you solve it, okay, ready. But again, I don't want to do offline solutions. What I want to do is, I want to learn in real time how I can place my actuators, okay? So, again, as I told you, I will define this as my temporal difference error, okay? And the easiest way to do that is by taking this, let's say, so you can think that this is an estimated form, not the actual one, because this is the one I want to find. And this is a temporal difference error that I want to take it to 0. The first thing that will come to your mind when you have something square is you can use gradient descent, right? So you can find this component, define a dynamic equation of this component to drive this error to 0, okay? If you do that, then you have something like that, okay? Again, this is a simple gradient descent on this one, but you see also this one is anormalized it because this will help us navigate stability in a better form, okay? So again, I have my temporal difference error, okay? And then I use gradient descent on that, okay? To find the unknown components, which is the hat here, okay? And then I find the tuning law for the p hat. And the sigma here is how fast I'm learning, okay? And this means that, of course, the larger it is, the better, but as an adaptive control, if you pick it too large, you can incorporate some oscillations to the system. So there's always a sweet spot there, okay? Okay, so of course, we know that the learning law that you saw before, this is a Frobenius norm, okay? So this Frobenius norm does not increase, and then also converges to 0, given a condition on precision of excitation, okay? What does it mean is that I do exploration exploitation by incorporating some noise to the control inputs, Okay, so I want to explore the state space. Okay, and of course these are tools that somebody can use from adaptive control. Okay, so in adaptive control, you want some waves to converge, and how you do that is by guaranteeing something that is called precision of excitation. Okay. So again, the precision of excitation is, it looks like that. Okay. And why I want to add this noise in the control input is because I want to make sure that this inequality is true. Okay. Of course, there are other ways that you can guarantee precision of excitation is by using experience replay or previous data. So this is something that is called, or we have called in our work as concurrent learning. So this means that I use previous data and current data at the same time to not require this very strict P condition. Why? Because as you can see, I have to guarantee that this condition is true for the future, for every time in the future. This is, again, this is adaptive control, right? So every adaptive control textbook, like by Ioannou, by Gang Tao, by all these people, you will see this condition, okay? But you see that this has to be guaranteed for the future, okay? So, but there are some ways that you can avoid that by using previous data concurrently with the new data that you get from your state trajectories, okay? Okay, so let's see how we can do that online now, okay? So you saw before that I have this gradient descent. So what I do, I wait until my P converges, okay? And then select the actuators, which can adjust them either offline or online, okay? So let's see what we can do. So at any instant, Tj, okay, I can always choose a set of actuators, okay? And this can happen in real time by solving this optimization. And what you see here is that the P hat that comes from the learning before is actually updated in some time instance, okay? So in other words, this J and this J, what this means is that I will find and I will select my actuators given some specific times, okay? I cannot, for example, change my actuators like every millisecond, right? I mean, this will never work in a real system. Okay, so this is a little pseudocode, so to put everything together before you see that. So again, I start learning the P bar, okay? I sort the values based on what is the best. I choose the actuators that they have the largest value from the optimization, and then I update my B metrics, okay? So again, this is the one fixed, and this is the one I can tune. And I do that for some specific time instance. Okay, so again, we have proofs for everything, okay? So, and I can schedule permanently infinite time. Okay, so let's see actually an example now. Again, I'm in aerospace engineering department, so I always have to put an example of an aircraft here. So, let's say I have this benchmark aircraft, which is Admire, which is by SAP. So this is a benchmark aircraft by SAP. So why we want to do something like that is because this by design has redundancy in your actuators. Okay? And you have 7 available actuators, okay, that you want to incorporate into your system. Okay? So, of course, I want to pick 4 of them, as you see here. Remember in the optimization, okay, I have to pick k of them, so here's 4. These are some tuning laws, okay? I update every 10J, okay? So let's say if I had the model, okay, and I can solve it offline, so then my optimal ones is to pick the 3rd, the 4th, the 5th, and the 6th, okay? So, this is my problem. So I want to see now if my learning algorithm, without knowing the model A and B, will actually converge to this optimal solution without any information. It will happen in real time. Okay, so remember that I had to estimate the entries of the P, okay, which is the Lyapunov function. You see here that eventually goes to 0. Again, this is the Frobenius norm, okay? These are all the components of the P. So this is the actuator selection, okay? Remember, which ones will we converge to? Let's go back. 3, 4, 5, 6, okay? So the green ones, 3, 4, 5, 6, means that 3, 4, 5, 6 were selected. So the green one means they were selected. The black ones means that they were not selected, okay? So, again, this is a comparison. This is the model-based one, the model-free one, and you can compare it with the offline one that you saw before. So again, you see that it matches. Okay? So, what we did here up to now is that we had the actuator placement without any adversarial input into the system. Okay? So, and I wanted just to quantify controllability. But of course, if I want to do actuator selection, and I have, let's say, some attackers that they can potentially make me choose the wrong actuators, okay? So then I have to adjust some things. Let's see what I have to do. So instead of having only this part that you saw before, okay? So I have an extra component, okay, which are adversarial inputs. So of course this becomes a zero-sum game now, okay? So the U is the minimizer, and the A, which is the adversarial input to the system that will make me choose the wrong actuators, is the maximizer. Again, you can see it convex on U and concave in A. So this is pretty straightforward. And then I have some extra because I want to move my equilibrium points around. Okay, so so again, I can solve this thing as an actuator selection problem without requiring A and B in real time. Okay, so of course we can similar with before. Remember, so I had the controllability gramian. So now, instead of having the controllability gramian, I have this something that is known as the game-based controllability gramian, which is again one extra term, right? So, so instead of working with the controllability gramian, I work with the game-based gramian. Same things with before. Okay. So what we did up to now is we developed a model-free, which to our best of knowledge is the first model-free actuator selection algorithm. We selected the actuators to quantify controllability resilience, and then we proved equivalence with the model-based. Okay, let's see what we can do. We can improve on that, okay? Because controllability was measured from before on average, okay? We can still do across closed loop trajectories now. So let's see what we can do. Again, let's say we have the same system, right? So A matrix, okay? V is my pre-specified control input, and again, A is my unknown parallel inputs, and G is my unknown input matrix. Okay? So let's see. So, of course, I can map actuators to controls, okay? And I can map any actuator to any control. So, of course, you can see that B here is the columns, as you remember before, that comprise the actuators, and U is the actuators commands, okay? That they move the things around. We can say that the system is redundant in actuators, okay? As you remember, I have more actuators than I need, and I want to incorporate it to my system if some conditions are true. Okay. So now, remember that I told you we don't do it average, but we do across trajectories. So then we change the problem a little bit, okay? So instead of doing actuator placement, we do actuator allocation now. Let's see actually what is that, the problem. So I only choose the U to minimize this energy, okay? So as you see, it's even simpler than before, but let's see what's happening.
The energy of the actuator, the energy of the actuator.
Yes. So I want to allocate the energy of actuators, okay? So this one is the optimization problem now, okay? So as you can see, I have a freedom a little bit here, right, with W. Let's see actually what we can do. Of course, this is a very simple optimization for now, okay? I can have a closed form solution, okay? I'm sure you can solve it here in 2 seconds. This is the closed form solution, and this is the optimal cost. But what I want you to see is the optimal cost has this extra component here. You remember before what we did, right? We played with B, okay? So if I play with B, then I can optimize the cost even more, okay? So this is exactly what is the problem, okay? So this is what I get, but I know how to optimize B even more, okay? So let's see how I can play with these variables now. Okay, so remember that I will follow similar things, but instead for, as you saw before, for the placement, for something that it's called in the control theory, optimal control allocation. So again, I have a B matrix, which is composed of 2 different elements, B1 and B2 as before, okay? So B1 has components, B2 has other components. Okay? So, from before, I have a fixed part and I have a choosable part. Okay? So, let's see actually what we can do. I only have freedom to pick the choosable part, okay, such that the minimum energy that you saw before is minimized. Okay? So again, still, this is something that I have to pick, okay, for now again, okay? But as you can expect, I can quantify this energy by incorporating this and playing with the things that you saw in the parentheses. So, again, these are just some assumptions, okay? So this is, we assume that the matrix B1 has full row rank, which is some assumptions that we need to have actuator redundancy, okay? So, now recall. Remember, this is my thing, okay? So, if my V is not fixed, right, you see here, I cannot find it. I cannot directly optimize this one, right, over B. So let's see what we can do. We can optimize though on average, okay? So instead of doing that, I can optimize on average. So I take this middle part as you saw before, as you were expecting this result now. So my optimization will be on this thing, okay? So let's see a simple scenario. Let's say first that I know V, okay? So I know V, and there is an initial condition distribution like that, okay? So let's see what we can do. So I can optimize the energy directly over infinite horizon, and I can choose my F to be that one. Again, you can expect that one, right? So remember, this is my LV that you saw before, right? So you put it here, and then this is actually the closed form one, right? And of course, my FB, if I want to solve it, when my V is known, it has to be that one. Okay. Of course, I can write this one in a static form using Lyapunov equations. So, here it is, okay? So, these two equations, they actually solve this problem, okay? For now, again, these are just some offline equations. They look like Lyapunov equations, that they're coupled, and they solve this problem. Okay, so, as you can see also, solving the trace of QR and solving the trace of PV is the same, okay? So, of course, there's some caveats, right? So solving by choosing f of b to be the trace of PV is inefficient because it has to solve the Lyapunov equations for all points into to the power set of s. Okay? So instead, if I solve the QR, okay, this requires a solution of only one Lyapunov equation for Q. So let's see. But again, what we want to do is, I want to solve this one model-free. Okay? So let's see again. This is my cost, right? And these are my constraints. Okay? Pretty straightforward. So, my A and G, okay, that they're the system, remember, the system that I had now is A and G. My P is just some added optimality that came up from the cost because I mapped my U to V, okay? You remember that. Okay, so A and G are the system dynamics. And they appear only on this equation. So let's see. So, again, we said all these things, okay? So again, we know how to solve all the Lyapunov equations model-free, okay? But as you saw from before too, this is a dual Lyapunov, right? For two things, it doesn't have a constant term, and the transposes are in the wrong part. So, what we need to do is, I want to turn it into a nominal one. So, as controls people, we like to multiply and divide or add zeros, right? So, so what we do is we will multiply left and right by this Q inverse, okay? And of course, I can do that because if I cannot do that, then the problem doesn't have any solution, right? And so if I do that, then the equation becomes like that. So you see that the transposes, they appear somehow in a better way, okay? Okay. Of course, we can solve any algebraic Riccati equation, as you see here, in a model-free way, and then I can solve it even with Kleiman's algorithm, okay? So, let's see what we can do now. This is just a simple policy iteration to compute this Q inverse, okay? So what this means is that I solve, I wait until this converges, and then I update it. Okay. And of course, we have a proof that, remember that because the transposes appear in their own way, this is not an actual Lyapunov equation, but it's a dual Lyapunov equation. So it doesn't require the system A to be stable, but it requires the system A to be anti-stable. Okay? That's why you see my A over there, my minus over there. Okay? And of course, this is very different because it doesn't have a constant term. Okay? So it's different than a conventional Riccati equation. So everything else now is the same. Again, remember that I converted this to an anti-stable Riccati equation, okay? And then I can put the known and the unknown parts in a vectorized form. I can call everything else an activation function, and I can solve it with your favorite thing. We can solve it with least squares, recast least squares, radius, and so on and so forth. Okay, so this is just some assignment of variables. Don't worry too much about those. Okay, so of course, in order for me to solve that, I have to guarantee some things which is similar to the position excitation conditions before. It means that I have some enough data to solve the problem, in other words. Okay. So, and again, after we can put everything together, okay, so you can have a model-free procedure to estimate this one. Everything is stable, okay? So let's see how this can work. Again, as I said, because I'm in the aerospace department, I have to put pictures of airplanes, okay? So let's say I have this eVTOL, okay, where it has 9 states and 5 high-level control inputs, okay? And I'm going to do, so actually, our control allocation is very popular for these kind of vehicles, okay? Because you want to allocate the control commands to the different parts of the system, okay? So let's say I have all these actuators here, okay? And I have an initial set, I think 2, 4, 6, probably I have like about 14, I don't remember, but you can count them. So the initial actuator set is 1, 2, 3, 13, and 14, okay? And I want to augment my matrix with 6 more to do optimal control allocation. And I want to do that in real time without any information about the system, okay? So again, we can have the cost function as you saw before. I can pick my parameters, okay? This is the noise that I can add to my control input, okay? So here on the left, you see the state evolution. You see that it converges to 0. This is the norm of Vt, converges to 0. And this is the convergence of the estimated one to the actual one. Again, this is a Frobenius norm, okay? So you see that converges to 0. And the result that I get by doing that is that the optimal one is this one, okay? And again, this happened in real time. So now, what I did for now, I designed 2 algorithms, right? One that does actuator selection, and one that does optimal control allocation, okay? And then all these things, they're in model-free way, and we proved it is a small disturbance input to state stability robust to input noise, okay? Okay, so several papers on that. How much time do I have?
About 10 minutes.
Okay, good. Okay, so now let's take it one step further. Another difficult problem that we deal with here is we want to do sensor placement, okay? Whenever you do sensor...
Can I interrupt?
Sure.
How about in the previous, I have a burning question.
Sure.
In the noise that you add in the control input, so what's the compelling reason to add the noise?
So this is the precision excitation condition. So you want to explore the state space, so you want to move around your control input to move away. It's like exploring the state space. Yeah, this is very... it started from adaptive control when you do tuning of gains online, because you don't want to get stuck in some local solution. So you move around so you can actually move away from...
That's why you use sinusoids. Right?
Yes, exactly. So you can pick sinusoids, you can pick anything. So adaptive control says that you have to pick different sinusoids with frequencies that they're independent from one another to excite the appropriate modes of the system. So, now, let's see how we can do sensors. Oh, by the way, we will do that also in the discrete time. Okay? So for sensors, it's even more difficult. Why? Because I have my output, right? I don't have complete information about my state. So somehow I need to find ways to do this in a model-free way. Again, in this one, I don't know A, B, and C again. Okay, let's see how we can do that. So as you saw from before, right, you remember the B's are the actuators, the C's are the sensors, okay? So, these are my sensors, right? And every component here has a dimension of 10, right? So, let's see. So, of course, I can choose something that's smaller than this P, right? Which we can call it P bar, okay? P prime, okay? So, from all this matrix, I can pick a subset of it, okay? So, again, before we chose columns of P, what we do here, we choose rows of C. So, again, similar with before, right? So, you know, what I have to do is, I have to pick a selection matrix, right? I have to pick a selection matrix to activate different parts of my C, okay? Let's see how we can do that. So, again, somebody can ask about observability. Of course, I know a sensor set, right? Such that my system, after with the choice of the selection matrix, okay, is observable. Okay, let's see what we can do. How do we define, though, the best sensors, right? Okay, so as you saw from before too, right? So before you had the U here, right? So the best sensors is by picking your Y's, okay? So very similar with before, right? So I want to optimize that, but now I want to maximize this H2 norm, okay? And then if I maximize that, it's actually equivalent to the trace of this, which is equal to the trace of that, okay? And of course, the WC and W0s, they come by solving these equations, okay? And again, your A is just a discount factor for now. Okay, so what I want to do now is I want to do that only with input-output data, completely data-driven, okay? So my problem statement then is to pick these S's such that I maximize this one here, okay? Which is this one, right? So remember my F before, right? So I want to maximize this. Okay, so as I said also before, in actuator selection I want my X, right? Here I can only measure partial state because I measure only my output signals, okay? But again, if you go to your undergrad controls class, okay, you know that you can reconstruct your state based on input-out, okay? So you can write your state as a combination of controllability, observability, and a top-list matrix with Markov parameters, okay? This is actually what it is, right? So, as you see, this is my controllability, this is my observability, this is my top-list matrix, okay? And then this is the way to write, okay? So zeta is all these matrices together, okay? You can see all the equivalences here. So, so you have a dependence on U, a dependence on Y, okay? So, and your zeta are all the previous inputs and outputs, okay? So, again, this one is a way to write your state with respect to inputs, outputs, okay? Again, pretty straightforward. Also, if you want it, I mean, you know the work of Willems, right? So Willems also does something like that in a different way with the Hankel matrices. This is not really a Hankel matrix, it's a top-list Markov with bunch of parameters, but same logic. Okay. So what we want to do is, I want to do input-output reinforcement learning, okay? So, and of course, I want to find the cost to do this optimization by picking this S gamma, which are the selection algorithms. Okay, so again, same thing with before. Okay, so I pick my basis, I pick my energy signals, I put everything together, okay, and eventually I want to guarantee that I take some errors to zero. Okay. Okay, so of course, in order for us to be able to solve this problem, which is you put things together with the outputs, right? So again, we want to solve the problem by using data from before, input-output data only. Okay? So of course we have to guarantee some conditions, okay? And then eventually I'm able to solve the problem. So let's see how we can do that. So first, by using only input-output data, I can define a greedy algorithm that will find the best sensors in polynomial time. So what we do is I start with a horizon, okay? So I pick an initial condition for my C prime, C tilted, which is the one that I want to pick with, okay? So I gather output data from the system, and I evaluate how good they are, okay? And then I sort them, and then I pick my piece, and I select my output matrix. Okay. Again, of course, we prove that this converges, okay, to the best set of sensors in the polynomial time. Okay. Of course, as you saw before, right? We did it for discrete time, we did it for continuous time. Of course, you can pick similar things also for discrete time domain to pick the sensors, okay? Of course, there are the metrics, okay, which are fine horizon observability metrics, or even more, to volumetric observability measures, okay? So you can pick different things to optimize. So let's say, so now, because my background is electrical, although I'm in aerospace department, now I have to pick something like a power system too. So let's say that I have this IEEE 39 bus test system, okay, where I have a rotor angular frequency, which are have 10 states each one, okay, so you have, this system is 20 states. Okay, so, and then I have 20 state sensors, okay, as you can expect. Of course, the algorithm I described to you is in discrete time, so I have to discretize the system and then get my discrete time equivalent. Okay, so initial set of sensors, okay, I start with is 1, 3, 4, 6, and 8, and I want to augment that with 7 more out of all this set. Okay, you have 20 sensors, remember? I start with 5, and I want to incorporate 7 more from the pool of 20 sensors in total. Okay? Actually, they're not 20, they're 15, right? Because I have already picked other ones there. So, so as I said before, I can pick an ending horizon volumetric cost with a discount factor, and I can pick a past horizon of 6. This means that how many data I will use before. You remember I had my controllability observer. I wrote my state with respect to previous data, okay? Which is observability, controllability, and totally matched with Markov parameters. So this means that I will pick up to 6 previous data. Okay, this is my past horizon. Okay, so what you see on the left, okay, so this is the estimated cost for all possible sensor sets, okay? And this is the estimation error, which is, as you can see, it's around 0, okay? And the greedy algorithm yielded an optimal sensor set, which is what I had before, but incorporated 1, 2, 3, 4, 5, 6, 8, 7 more sensors, okay? And then it improved the controllability, the observability of the system. Okay, so so what he did in this work, right on time, we showed how reinforcement learning can be used to select sensor and actuators. We approached the problem in continuous and discrete time systems, and we used state and output feedback. And of course, we have tested it in very large simulations, and then I think my student, actually now, is a postdoc. She used it, even tested it with 100 states, and it had very fast results. And then with that, again, of course, I'd like to thank my student Philippos for doing all the work, of course, my funding agencies, and Andres for the invitation. So thank you very much.
Great, thank you, Kyriakos. Any questions for our speaker? Yes, fine.
I have a question on the second conclusion.
Sure. Let me go to the conclusion.
No, I understand the actuator selection problem as an offline problem. You solve it offline, you find the best actuator setup in an optimal way. And this also applies for the sensor selection.
Yes, good.
Why are we interested in solving this online or model free?
Because usually you don't have any information about the system. So let's say your system, let's say you fly an aircraft, and every time your mass changes, your system A changes. Okay, so whatever you have computed offline is not optimal anymore for your system. So in order for you to get another, you have to call your computer down, you have to recompute your gain, and then send it back to your aircraft. Let's say this is a simple example. But usually in real situations, you cannot model the systems. Okay, so in other words, A and B is unknown to you. So that's why, and also everything that you compute offline works only for these specific situations for specific system. And also you cannot change, for example, you do real-time anything. So for example, in optimal control, you can change Q and R, but you have to do it only offline. If you do it online, you can change Q and R in real time. and then you can improve performance depending on what you want to do, how you do it, and so on and so forth.
Can I do a follow-up? So
Sure,
these
sure, sure.
algorithms, these algorithms, they converge to the optimal actuator setup.
Yeah.
So at every iteration, there's a new actuator setup.
Yes, but at the infinite, I mean, the solution to this one has only one unique solution at the end.
Yes, but changing the actuator setup from one iteration to another, how is this applicable to an online setting? In a robot, for example, online. You can't change the actuator setup.
So let's say, again, for a robot, let's say you have multiple actuators that they control your legs or something like that, right? So you still have controllability, you can still move around, okay? But because you have a redundancy, okay, you can always find the best combination of these actuators to control your robot.
So this applies to the, you have a fixed actuator setup,
Yeah.
but you find the optimal control inputs to these actuators.
So you pick
Or activation.
the,
Or activation.
yeah, activate the other actuators. So you find
You
the-
have your structure, it's fixed,
It's fixed.
but you can activate some of them just to increase your
on controllability or observability
Perfect.
to make it more optimal, energy efficient.
Perfect, this is clear.
Yep.
Which means, practically speaking, is like, change the location. Right?
Yes, yes,
but
yes.
The figure by, that's a virtual like.
Yep. Yep.
Okay, thank you.
Any other questions for our speaker? Yes.
I'm trying to see, it's kind of a follow-up for the previous questions. In the first paper that you showed, we saw that we had, as you said, a finite number of actuators. I'm trying to see how this can work when the number of actuators increases a lot, or if, I'm not sure if I can find an example, or if we can have an infinite number of things we can do in terms of number of actuators. I mean that this is probably not the case, because when I have a system, I have standard actuators. But as you saw previously, the helicopter,
The eVTOL.
yeah, it was
Vertical
something that
takeoff.
the actuators started getting a lot.
But I know how many they are though.
Yeah, exactly. My question will be how this can influence the learning, because the more actuators I have, it might be the convergence.
Yeah, it will take more time, and yeah, of course, because this increases in a polynomial time. So the more actuators you have, the more time the learning will converge. Yeah.
Exactly.
Yeah.
And so if you do that online, this time, probably my insight is that may influence a little bit the system. If you have a lot of actuators, that you may have some kind of deadlocks. I mean, like.
But remember, I have a fixed one in the beginning, so my system is already working. What I want to do is I want to improve the controllability and observability of the system by incorporating more. The system is already working properly because I have a fixed one that already makes the system controllable and observable. So it can work with those. But what I want to do is I want to incorporate more that I have available, because nowadays, I mean, especially in CPS, you have redundancy of session actuators. So we want to incorporate this knowledge and then try to improve things. But the system is already controllable and observable because we have this fixed part there.
So even if it takes a little bit of more time, it's not
Still working.
Yeah.
Yeah, yeah,
That-
yeah.
So we're running out of time, so let's take our speaker again.
Thank you very much, everybody.